Okay, welcome back guys. So lesson 6, this is on elastomers or rubber-like materials, and as we discussed in the theory part, this would be more towards using the Mooney-Revlin constants or Mooney-Revlin material model. Okay, there were 2 to 3 different material models which could be used for rubber. The other ones were Ogden and Blasco, but in this case we are using Mooney-Revlin, and we'll see how we can take the stretch to strain graphs and imbibe in the software, as well how the Mooney-Revlin constants are derived and they are implemented further. So obviously the material data should come from experimentation, so that is what is present with us, and if I have to quickly show you that, it is somewhere in the same place where we have the files given to you. So they are kept, I guess most of you know the location of these files. So you'll find these test data. One of them is the uniaxial test data. We have other uniaxial, planar, and there is one more biaxial. So these 3 test curves are there with us, and we are going to utilize them to derive the constants. We'll analyze the effect of having an appropriate number of constants, that is what happens if you use 2, 3 and 5. We'll also see at the different behaviors if you use only 1 curve, 2 curves, or all the 3 curves. Okay, so interesting chapter. The example over here is quite a simple thing. It is a thin rubber pipe. Okay, thin rubber pipe clamped at both the ends and is subjected to a pressure of 25 psi. Okay, it is internally subjected to a pressure of 25 psi. Let's see what else we do in this chapter. Obviously a huge amount of theory involves, and that has been discussed in the one of the original recordings or the previous recordings. Please go through it, as well as read through the text of this particular training manual, especially the first initial part on the theory part of it. So as mentioned, we are looking at a few different scenarios. One of them is 2 constant Mooney-Revlin, another iteration with 2 constant Mooney-Revlin but using 2 material curves. So previously in the first iteration we are using only 1 uniaxial curve. In the second iteration we are using 2 curves. In the third iteration we are using 3 material curves as well as 2 constants, and finally 6 constants and 3 material curves will be used, and we'll see the difference, how accurate those can be. Okay, to start off with the setup, let me get into the software. We are creating a nonlinear study, simple nonlinear study. The name given is uniaxial test data. This part is being modeled using a shell element. We are selecting the appropriate surfaces to represent as the shell. Okay, these surfaces are given a thickness of 0.75 millimeter. The mid surface is used to represent them, and I believe we are all comfortable with this particular definition. The part is fixed at 2 ends where it is being held, and the internal pressure of I think it was 15 psi, something like that, is applied on this particular surface. Okay, it is a constant pressure. Now the new things that we learn or are going to use over here are these, wherein we are going to create a new custom material property. I guess most of you should be aware of that, how to do it. So right click, new library, thereon we create a new material and we get this particular uniaxial material. In this particular material we are going to select the material model to be hyperelastic Mooney-Revlin. Okay, we are taking the Mooney-Revlin material model. We are in the first iteration we are taking only 2 constants to be calculated for the curve. The constants should be calculated from the curve data, so we select just the checkbox. The only different things that you might want to enter is the Poisson's ratio. If thermal is there, a coefficient of expansion, so no thermal here, we can neglect it. The density and the tensile strength. Okay, let's go to the curve. So over here the simple tension curve has been given. Okay, this ensure that the appropriate units are selected properly. In this case, it is Newton per meter square. If we get into this one, the curve, if I select file, typically it permits us to import a CSV file or the curve data. It could be in the ASCII format in either a notepad or even Excel CSV file can be read directly over here. So you need to just browse through the proper location and give the file over here directly, and the software can read it for you. So it is already by the way, you can even copy paste the file content here, even that can be done. In this case it is already read here, so I'm not going to do it again to overwrite it. So this is the way that particular curve looks. So this is the curve which is coming from the practical testing. It is a curve between stress to stretch ratio. So this particular iteration, do you want to say no? So this is done. In terms of properties of the study, no big differences. We are selecting, we are taking the default values. Only the solver is FFE plus here. Large displacement is used. There is no particular reason for using FFE. It is just a different option that has been selected. Okay. So this is what it is. This is the setup. We can solve it, and there are different results that you might want to see, but one basic thing could be this particular displacement, maximum displacement, which is in the tune of 2.27 millimeters. Okay. Excuse me, sorry. In terms of result options, no, this is not relevant. What else is important that I need to highlight? Okay, the other important thing could be, now we saw that we are giving, I'm sorry, let me open the material property thing here. We saw that we are giving the curve down here, and these two constants are calculated by the software. If at all you want to see what exact values it has calculated, then you can go to the location where the file set is kept, search for a few different files, like a file by extension PLT can give you certain things. There is one more file by extension, what is the name, I forgot, lag file, and there is also one more file by name log file. Okay, so any one of them, first of all, the log file can give you these constants. You can see here the Muni-Revlin constants. The log file is somewhere here. Okay, this file has those constants. You can see it over there. These details can also be seen in the log file. Okay, so these are the constants calculated by the software to derive the curve as and when it solves. Okay, saying that, one more important aspect would be, so typically we are giving a certain set of curve to the software, which is converted to Muni-Revlin constants and an equation, and further that particular curve will be used by the software to do the calculation. So obviously we want to see what are the values that would come up when the actual curve is converted using the equation to a new curve. So those values can as well be seen in a file by name .plt. Again, it is a ASCII file. You can open it using Notepad. This file can help you visualize what is the difference between the actual curve and after the curve is being represented as a equation using the Muni-Revlin constants. Okay, so this is what it is all about. This is the way the setup is created. Let me go through the text in the training manual to check if there is anything that I have missed out. So we read this one, create mesh, set properties, run the analysis, review the results. Yeah, we saw that the deflection was around 2.27 millimeters. Reviews, yes, as I told you, we can check the lag file or the PLT file. Okay, both will give you the values, as well as the PLT file has the comparison of the theory versus practical. These curves, if you want to compare, you can plot them into a graph either in Excel or somewhere, and you can visualize it. Let me check something here. Okay. Okay, this is what we saw. This is fine. Okay, all is fine. Hence, it is necessary. Yeah. So now we'll move on to the two curve models. So let's move to the two constant Munir-Evelyn model here. Now the only difference here is we are giving two material curves. Let me activate that particular study. Let me go to the material properties. So this remains the same, whereas when we go to the material curve, we are actually reading two curves. One would be the biaxial tension and the other one would be the simple tension. Okay, these two curves have been given to the software, and we are keeping the number of constants to 2 itself. Okay, and further the analysis is done. Even with this thing, you will see a considerable difference, that the deflection will drop down from 2 point something to 0.57. Okay, it's a big difference. Further, if you move to one more iteration wherein we are again using the uniaxial biaxial planar thing, we are as well giving the third curve, and we are using at the moment I think we continue with the two constants. Okay, and the analysis has been done further. We get a particular result, so it is almost similar, but a small difference has come up over here. Finally, we change this. The number of curves is 3, so no big difference. However, the number of constants that is used is 6 actually. We can change it to 6, and we do the yeah, these three curves have been given. These three curves have been given. Okay, let me apply this. Close. Oops, no, I need to change it to 6. Yeah, apply, close, and you can actually solve this setup. It's quite fast. I'll also check this one. Yeah, I think this one was not actually 3, so I would like to make this 5 rather. Yeah, 5. Let's try something more and as well solve this with 5. Okay, while this is solved, I can go here and check the stresses down here. Okay, displacement. What's wrong? Okay, so both these studies are done. My concentration is on displacements. Oops, it is that solving, I guess. Is this done? No. I did something more. Let me solve this again. Let me solve this again. Okay, so the solution can be done with multiple constants. That's what we saw, and actually when we are using 2, it is the result has further gone down. But moreover, why it has gone down? One, because it is difficult to interpret just by the change in displacement on if it is improved or worsened. The better or important thing would be the comparison of the derived stretch to strain curve compared to the practical curve, and that can be done by exporting the PLT data into an Excel sheet and done. But obviously, if you have more the curves, better, more the constants, better. We are looking at a more accurate solution. Okay. Saying that, if it is a bit time consuming to convert or export the data from the PLT file to Excel and compare. So we'll directly see it in this particular training manual itself. So if I scroll through this, second iteration is obviously biaxial tension, where we are selecting the curve is already given and we are just solving it. we get a, yeah, here is the comparison. This gives a better view. So yeah, it looks okay, but can be better. The pink curve is not very matching to the blue one, which is the practical curve. The third iteration is more from 3 material curves and 2 constants again. So that's what it continues, and let's see how it goes on. The curve, yeah, the deflection is 0.58, that's what we saw, and frankly not good enough. So 2 constants with just increasing material curve is not good enough. It does not appear to be matching. Thereon we increase it to 6, the final iteration with 6, and here you go, it is absolutely matching. So when we see it, obviously with 6 constants, the curve is far more accurate. The Munirulin has calculated this curve in a better way than the previous 2 iterations of 2 constants. So this is what it is all about. This is an interesting, I would say, phenomenon wherein we convert the given practical data into a equation which is using the Munirulin constants, and further the simulation is done using that particular equation. If you want to do or ensure that whatever the constants that it has calculated are accurate, then you can do or follow the steps that have been given in this chapter. If not, obviously you can take the maximum things. Hopefully you have the data for all the 3, and we can continue with it. That's how it all looks. Fine. So yes, pretty much that's it on elastomers. In the next lesson we'll move into a bit of contacts in nonlinear,